I'm Konstantinos. I'll be talking to you a little bit about some high-altitude balloon payloads and what Rust kind of as a software development practice looks like and how that benefits students in creating a little bit more of an ambitious project. And I'll talk to you a little bit more about where Rust really shines and maybe some places that it doesn't so much. So first, I'm going to talk a little bit about myself. I was involved in some space grant projects at the Arapahoe Community College in Colorado. It's all coordinated through CU, and now I've transferred up to CU to study electrical and computer engineering. So I was part of this DemoSat program, and I was a team lead for about a year, and I was part of some other projects before that. So this is the space grant, and those are the schools. And then this last little logo in the corner here I want to shout out is EOSS. Edge of Space Sciences does our launches for the balloon projects, and they coordinate all of the hydrogen to get us up into the air. So before I jump into anything more, I want to talk a little bit about microcontrollers. Traditionally, this kind of project uses an Arduino based microcontroller, and that's very common in this kind of education space. That's actually spoken about a little bit at GPSL, which is a name you might want to know if you're interested in balloons. It's a little conference that happens out in the Great Plains, and they talk about how they wanted to move a little bit towards Arduino so that more people could be involved in creating this kind of projects. So AVR, which is what Arduino runs on, is possible with Rust, but it's very different, and so that's kind of out of scope for this topic. I guess my assertion here is that you should be making the jump up to 32-bit microcontrollers to open up a world of possibilities. If you don't believe me about that, then kind of the rest of the presentation won't make much sense, but 8-bit microcontrollers, I'll say, are starting to feel maybe a little bit retro, and that jumping up to 32-bit lets you feel a little bit more, it lets your code feel a little bit more like code on a standard platform, like a desktop or something. And then you get some speed and some features along with that, and we'll talk about the world of possibilities that this opens up on a later slide. So what is a high-altitude balloon? I guess I should start with that. I'll make a distinction between kind of two different kinds of balloons. Over here on the right are what I'll call this like traditional heavy balloon. You send it up to about 100,000 feet up to the stratosphere where it pops, and it comes back down. Your flight is a few hours, and we usually launch these from eastern Colorado, and we try and get it just within the Kansas border, so not very far at all laterally. But these balloons support thousands of grams, and you have these payloads that have a little foam box that contains all of the batteries and everything else. And then this newer, and I think arguably more exciting kind of balloon that people are getting into is Pico ballooning. Actually, here is Bill Brown, who I mentioned on the other slide. He's a big proponent of Pico ballooning in education. And these balloons, they don't go up as high. They go up 35, 40,000 feet, and they chill in the jet stream. But they've been known to circumnavigate the globe. The one thing about these is that they're very small, so you can't fit a whole lot of payload on them. Batteries are kind of a no-go. And so these actually use supercapacitors and solar panels to come online when the sun is up and transmit data. And you don't recover these because you don't know where they're going to land, probably not anywhere easy to get to. So you only get a few dozen grams in weight. Oh, here's a little video of one of our balloons launching. You can see those little shimmering payloads. Each one of those is like a different student project. So I want to talk a little bit about like what the payload looks like. And I think the first place to start is where does your data end up? We, for a lot of these projects, use this little board from SparkFun. It's called the OpenLog. And kind of arguably, it's the smartest guy in the room for this kind of project. It uses the same processor as an Arduino, but maybe a little bit more of an intelligent code platform than we use in our student projects. But this lets us just send all of our data over serial and entirely forget about what does it look like to save data, because that's actually a really complicated problem, and it's probably a project in and of itself. This means that we just get to like print line or like serial.log it, and then it shows up. And so we just like make this like fake CSV file format. This only works for those like heavy balloon payloads that I showed before, though, because you have to recover the SD card. You have to recover the SD card arguably from somewhere dry, otherwise it's not gonna work at all. I'll talk a little bit about RockSat, who is like a sister program to the DemoSat program. They send a payload on a sounding rocket, and that lands in the ocean. And so for the last, I think, like few years of RockSat projects, they've gotten no sensor data back because the SD card gets destroyed in the salt water in the ocean. So this is only something that we get to do because of where we land. Here I'll show kind of what some of these payloads look like, and I really just want to highlight kind of the manual of operations. Over here on the side, there's like a switch. You have to be able to just flip a switch and tell at a glance, is this thing working, or can we like emergency fix it right now because it's about to go in the air? Here, actually, you can see our little open log there. And so that's why it's got street glow, is that it's that we have LEDs to signal, is it on, which is like a flight requirement, and is it working, which can start to get a little more complicated, and we'll talk about what that looks like in code. Here's some LEDs blinking. So what's on a student computer is also kind of an important thing to talk about. We talked a little bit about what these payloads look like. I guess one more thing I'll mention is that it's kind of just a lot of sensors, and we just dump it into an SD card. And so that's where our code comes in, is we're facilitating that. So what's on a student computer? Every student I encountered used Windows, with like a handful of exceptions, with some people with Macs, and they're easy. Those people are easy to work with, and like not even worth like mentioning, that it's just like they'll figure it out. They understand their computer well, and it tends to work easier on the Mac. You need a Mac or a Windows computer. Unfortunately, like Linux is not something that's happening in these institutions, because you need Microsoft Office. It's like a requirement for most of the classes in community college. So these Windows computers, they're set up with VS Code usually. Even if people have taken CS classes, they like are not set up for development for some reason. So they're down to install some extensions, but people do want to like manually operate their toolchain, and they want to see like how the bread is buttered, I guess. And then one last shout I'll give is like about Git. Git is kind of a problem with students. It's like they don't teach it in school, and so like everybody kind of understands what it is. And so it's like, I know that this is kind of a joke XKCD, but I really honestly recommend that you do this, is that it's just like have people force push their stuff to like GitHub or whatever, and just like don't worry about like the cleanliness of your repo, because the alternative is that everyone's gonna post their code in Discord or Microsoft Teams, and that's not version control. And so I guess all of this is to say that tooling and compiling stuff actually gets to be a real issue on student computers. Actually, one last shout is that, like, just to shout out another Rust project, is JJ actually might make some of this Git stuff a little easier. So if anyone's familiar with the Jiu-Jitsu project, it's kind of cool. And I think Zed is actually working on something that's like trying to fix some of these issues with Git as well. So if that issue is getting fixed anywhere, it might be in the Rust ecosystem. So I'll talk about some of the things that were specifically issues with Windows. We had issues with embedded GCC, MSVC, make, CMake, SSH. which kind of becomes a problem when you're using like traditional Pis. I'm talking about microcontroller code here, but like the USB drivers and stuff gets really to be a problem. It's difficult to get people's Windows computers talking anything but like standard like data transfer. Like definitely no IP over USB. It's like a big problem. And so you end up with these like long instruction posts in your Microsoft Teams chats. Like this is all the things you have to do and type into your console or whatever just so that you can even get connected. And that's a real bottleneck when you only have weekly meetings and a semester to do a project. Python is one more thing I'll talk about kind of later. And like the VS Code environment and environment variables are kind of related to that. I'll just give a little shout at the end about Python because we use Python to analyze our data and graph it at the end of the project. And so this is where Rust comes in. We sidestep a lot of the major pain points by just including a Rust toolchain.toml and config.toml, which you might not be familiar with if you only write for like a desktop environment. But this lets us just define what microcontroller we're compiling our stuff for. And you don't have to have students worrying about downloading which version of GCC and trying to install stuff. So I talked about a world of possibilities with the microcontrollers stepping up to 32-bit. And these are kind of the main ones that we considered. It's like every time we would do a project, we consider like, hey, are we going to do some C or C++? It's what's taught in the classes. It's like the industry standard, and it's very familiar. And so surprisingly, even people who've spent like a year in classes taking C++, it's like there's a lot of hurdles to clear to even get them to compile a program for a microcontroller. So this is actually kind of where the impetus for me to write this talk came, is some students were trying to compile C and C++ programs. We spent like probably 2 or 3 of our weekly meetings, kind of a lot in a semester, to just get a program running, just flash an LED. And you can see why that might be a problem when you're trying to do a more ambitious project. So we tried some like Rust, and a student said to me, why was that so easy? And that was something that I was not familiar like hearing about Rust. You know, Rust has kind of got a reputation for a little bit of a learning curve, but the tooling really makes things go very smoothly. Even compared to like CircuitPython and MicroPython, some of those issues I mentioned with like USB on like Windows computers can a little bit be an issue. It doesn't want to talk to your Pico or whatever. And this is a little bit of a step in the wrong direction for us. We wanted to get a little bit more into the nitty-gritty of what does the code look like, what's happening on our microcontroller, and we want it to be a little lower level, you could say. So Python is a little bit of a step in the wrong direction. Another shout I'll give here is that Jan Matejek at PyCon gave a very interesting talk about writing Rust native modules for these kind of embedded Pythons. And Rust native modules for Python has become a very hot topic. I think there was a talk about that earlier yesterday, or at least some of the talk was about that. So errors. Errors are kind of one of the big reasons that we use Rust. Here's a comment from one of our first Arduino-based projects. You can see that like having to put this at the top of your code to like decode what is our code doing might be a problem with some inexperienced students. And you have errors. Like definitely you have errors. I've never seen a project that just like works especially like in the balloon stuff. We had some like strange issues with like having the proper reference voltage for our analog to digital converter, if anyone's familiar with some Arduino stuff, that getting the supply voltage or just like the wrong wiring can be an issue. A lot of students don't know how to solder as well as they think they do. Not to like shade anybody, but it's something you have to like recover from, and like you have to notice. And if your payload isn't telling you until you can take it apart, like you have to actually peel tape off of the side of your box and go dig out an SD card. And then it's like, oh, we had an issue. You are wasting a ton of time if you can't just tell that you have an issue off the bat. So there's some philosophies about error handling. Let it crash is something you might be familiar with if you've played with some Elixir or Erlang. That's a very, it's like a mantra in that world almost. And we have to do a little bit of letting it crash in the balloon world as well. When you run out of power, or when like things just cannot continue at all, it's best to just let everything shut down and bring it back online in order to just start again and start collecting some data, hopefully get some information for the rest of your project instead of just being out of luck. And then you have to recover gracefully as much as you possibly can. There's enough that can go wrong in the physical world that software is not what you want your problems to be in terms of failure. And then one more thing I'll talk about in this world is that Arduino libraries all kind of have a different philosophy of how are we going to give you data, especially if that data isn't actually there. So sometimes they'll give you like a sentinel value, like a -9999. Sometimes it just like fails quietly. 0 is a terrible value to give in error contexts, and lots of libraries do that. And so anyone who's familiar with Rust will know that the result and option types are a huge boon in that world. So here I'm going to show you a little bit of the Arduino code that comment was from. And this is just kind of our error handling code. I hope it's visible enough. You don't need to know exactly what's going on here. I just want to highlight that we're doing a ton of these bitwise operations to kind of mask out our error codes. This isn't something I personally wrote at the time, and I thought it was very Lua hackery because one of the people on our team was a Roblox hacker. And this felt very appropriate for that kind of thing to me. But you'll notice that kind of what we're doing is like hand rolling our own very strange enum almost, if you kind of are familiar with how an enum works or are seeing kind of what this is doing. So it's messy, it's hard to understand, and you'll notice that we have all of these big long comments that are explaining like, hey team, don't get too scared. This is all this does. Here is the beginning of our loop where we're going to call that function from before. And so, I mean, look, it's like we kind of have like a match statement almost, but not really. Again, we're doing these kind of bitwise operations to like mask out our error when we could just be describing that very literally with Rust. And this is the first thing in our loop. This is before we do any logic. It's like we're already like this deep into our function without doing anything yet. And then just like this last little bit of code from like way deeper in the loop, and I have the comment from it as well. But just to show that like this kind of error handling really pollutes your entire code base. And I hope that anyone familiar with Rust's philosophy of handling options and results sees how that can be avoided. Next, I'm just going to talk a little bit about the Rust projects. This is a screenshot from, and the next few slides are also screenshots from a little README I made for my team. Just an anatomy of a Rust firmware is what I called it. So above these pluses, above this line, is just that's your standard Rust project. When you type cargo new in the terminal, it'll show you that. So below the line is stuff that we add for an embedded context. A lot of this is optional. A lot of this gets provided to you by the people writing your hardware abstraction layer. because we're not going like straight to the registers and the bits here. We have a semester to do a science project. So here, I'm just showing you a little bit about like what goes into a cargo toml, or not cargo toml, but config.toml to configure cargo and Rust toolchain. We are using Rust up. I know that some people prefer to avoid it, but it does so much for you, and students who have never been exposed to Rust, we don't have to talk about why you might want to avoid Rust up in that scenario. So here, we just describe the target triple. It's like, hey, we're having a RISC-32 microcontroller, and this is the form of the binary. And then this runner line is actually awesome. We get to configure a program that we get to run when we type cargo run, like you would for a standard program, except this will just like flash it to the chip for us. And so this actually gives us a very much similar feel to the run button in your editor, especially like in an Arduino IDE context. And then we had to use a nightly tool chain because like some of this stuff is experimental with these RISC chips. And that's not uncommon in the embedded world, is having to use nightly tool chains at the moment. So this is kind of a worst case scenario actually for what's in one of these embedded Rust projects. I'll go back here and just mention the build script and the linker script. That's what the memory.x and build.rs are, this opposite order. This is something that your most experienced Rust programmer will write once, or will be provided to you by somebody else who's already gotten code running on that microcontroller, and you're never gonna have to touch that again, hopefully. So students will not need to worry about those last two. And then here's our cargo toml. This will look very familiar to people who have written some Rust before. One thing I'll shout is that because I talked about how Git was kind of an issue before, vendoring dependencies is like a real big problem writing C and C++. I'll mention that the Pico toolchain, which the Pi Picos are known for being a very like user-friendly microcontroller with lots of documentation, but then you have to make a Git submodule to vendor your dependencies, and it's like, how am I going to explain a Git submodule to people who've never used Git before? And so we just put the link, and that's it. This star thing might look scary to people who have never written, or who've never encountered it, or who just like write a lot of Rust. It's like, you know, you're not really supposed to do that, but all three of these libraries are from the same place. Again, this is like for the most experimental of community support only microcontrollers. And anyone who's tried to poke around with these CH32 microcontrollers knows that writing C and C++ for them is a real headache. You have to download like some strange Chinese IDE to like compile the code even. And so this is like a community supported project, and it's actually really awesome because these chips are cheaper than Arduinos and other 8-bit microcontrollers. And then this last little bit I'll give a shout out to is essentially just the recommendations from min-sized Rust, which is kind of the Bible in terms of embedded programming. You need your code to fit inside of the flash that's available. And so we just minimize the size with some things to tell our compiler. Okay, and then next, that's a Rust program. This runs, and this is the kind of like worst case scenario for a hello world. So I'll shout out a couple things here that might look unfamiliar to people who have never written Rust in this kind of context. We're in the no standard. We don't get the standard library, which sounds kind of scary, but libcore actually gives you like a ton of the stuff that you would want. It's mostly just like stuff that doesn't let you allocate. And you can bring allocation back very easily with just like a little block of memory. And we really want to avoid allocating in these kind of projects anyways. No main might look kind of weird because we have a main function right here. That's just because we don't want Rust to give us the entry point that it normally does for like a standard target. We're trying to define our own entry point because we need to tell the microcontroller where we're putting our code. Everything else, I think, should look familiar except for down here at the bottom where we define our own panic handler. This is the laziest way to do it. There's lots of, you can just like define this in your cargo toml and just like be done with it. Or you can write your own error handling for panics, which is kind of a really awesome thing to be able to do in this kind of project, because when we want to crash hard, sometimes we can write some code that'll make things easier to recover when we want to boot back up. And then everything else, it's like this just comes from a hardware abstraction layer. This is just like a crate that gives you like the peripheral access. You're just like calling out pins and you're setting them high and low just like you would on an Arduino. I don't know, I think that some of the ergonomics of this are a little bit nicer than Arduino's way of doing it. And it'll look very familiar, I think, to people who've even seen C++. And I guess the last thing I'll call out is that exclamation mark. You don't want your main function to ever actually return. You want to just keep running your code. And so this is a little bit of the setup and loop that you might see in like an Arduino program. I'll talk a little bit about this, but I don't want to linger on it too much. I think Rust gives you a lot of kind of the clean code ideas for free. And clean code in a very loose way. I'm not talking about like the Uncle Bob book. I don't know, Nick Barker wrote a very nice C library for doing like visual stuff. And he's made some like very interesting videos that kind of went viral. And he just talks about his philosophy for like writing some decent C. And so like most of this stuff is just like given to you for free in Rust. So he talks about like C99 and using the standard int header instead of having to like know what is a long, what is a short, is it different than a long and a short on another platform, what's a short, long, long, like it's kind of a mess. So just calling out like int32 is actually like avoiding so much confusion for students who have not been exposed to those kinds of things. Preprocessor and includes are like where a lot of C gets messy. And so we don't have to worry about that. We get to like namespace things appropriately in Rust and include things appropriately. And we don't have the same like crazy preprocessor macro situation as in C. A lot of the recommendations are to keep things to a simple macro, which is like basically what Rust gives you. And then things like bounds checking and memory safety. These are huge in like in this kind of mission critical, you only fly one time. And so if you have a memory safety bug that it's like you're only going to find after like the third hour of a flight, it's like you're everything after the third hour is like nonsense in your program. And so a lot of these things about memory safety are given for free. And similarly with like the NASA power of 10 rules, NASA sets out some guidelines for writing C in a way that's appropriate for mission critical space code, and we're a NASA funded program. So we try to adhere to some of those things even if it's not necessarily like required for us. And so here's this screenshot of that from Wikipedia. You'll notice that like a lot of these things are also free in Rust. And the things that aren't are really easy to lint for with Clippy. That's actually another big thing, is that it's like we're getting real tooling when we switch to Rust, that it's like that being able to lint for stuff, like we were not linting in an Arduino program. This lets us ensure that our code is a little bit cleaner and a little bit safer than it might have otherwise been. So all of that is to say that Rust is like very nice for these kinds of projects, but it's not always the right pick. And so my assertion will be that these Pico balloons, Rust at 40,000 feet, might be actually cooler than Rust at 100,000 feet. It lets us circumnavigate the globe, hopefully. And so these are kind of the places that that it's been helpful. We can use like really low power, very cheap chips. You're not getting your Pico balloon back, so your budget is going up into the air and it's disappearing. So we want to be able to use like low power and low flash chips that enable us to do the project very cheaply. Rust shines there. I compared two comparable Arduino and Rust programs, and I found that the Rust program only ended up being like 10 kilobytes in flash, and the Arduino was like 30. Excuse me. Telemetry is a must on Pico balloons. You're not getting the SD card, so you have to like send the data, and that gets like really complicated unless you're bringing in a library to do it for you in Arduino. And so you can bring a library in to do it for you in Rust too, but if you want to write your telemetry code, Rust lets us define our data a little better. Last thing I'll mention is that you might want async, and that's where Rust is like leaps over Arduino. It's like if you want this kind of asynchronous programming, then like Arduino is not going to do you any favors. But you probably don't. Keeping things simple is like way more important than doing things in like the absolute best way possible or most efficient way. We have some cycles to spare a lot of the time in these projects. And so it's like we can just wait around a little bit instead of complicating things with async. And I think if you really cared about async, you might want to be at the other talk. Async canceling, seems like a very interesting topic. And so, yeah, I'll just mention this one more time, really hammer that home, that like there's so many physical failure modes in a balloon project that it's like the absolute last thing you want is to be like, oh, everything turned out great, except our code broke. So just totally avoid that. And then one final little note is Python. We get our data back, and we graph it with like a matplotlib script. It's always some random assortment of like pandas or NumPy or whatever. And I watched some like really kind of frustrating stuff where it's like students were unable to run their own script on their own computer because like they were having issues with the environment. So it's like, is this installed to the system Python or some other Python 3 installation? Are you calling Python 2? Kind of all a mess. And so I had to beg some of my friends in that group, like, please just use UV. UV really solves a lot of it. I don't think you need UV poetry or something like that. Works just as well, but I think UV is a really awesome set of tools that fixes a lot of the issues in the Python ecosystem, especially the works on my machine problem, which is a real mess if it doesn't even work on your machine. And then, I don't know, there's kind of some cool Rust libraries as well. Polars, it's like, I don't know if you wanted to switch out pandas for some reason. It's kind of cool, but I don't know if I'll recommend that. And then the last thing is, in our first project, that we did, our launch ended up being on the exact same day that we had to present at the symposium. And so we were trying to figure out how do we coordinate this so we can at least get some of our data to show. We considered it kind of, things ended up working out better for us where I think symposium got delayed or something. But we had considered using a WebAssembly library with Rust to plot our data instead because we could just very easily throw it on a website right away. Plotters is kind of a cool library for that. I think that's it. I'll just give a shout out to some of my advisors on the project, Tipsword and Professor Jones, and a big shout out to the team and the people at EOSS for enabling a lot of the education that I received. Thanks. I'm ready to take some questions if.
Thank you. Unfortunately, we don't have time
Sure.
for live questions, but please ask Konstantinos questions on the Discord talk channel. Thank you.
Yeah.
That's a great talk.
Thank you. I'll be on the Discord. I'll love to talk about balloons anytime. So, yeah, thank you.
Let's do another round of applause.